Hello, CUSEC 2022. I'm excited to be giving my talk today about game development in Rust. I've changed the title of my presentation from the schedule, since this is a bit more fun. So, let's dive into leveling up game development with Rust. So, first off, hi, I'm Forrest. This is my 4th year at CUSEC and my 2nd time speaking. I'm a student in Ottawa at Carleton University. I'm studying computer science with honors in game development. I also love working on open source projects, and I'll share some of them with you in a bit. I'm also a Rustacean. I'll have my Ferris mug right here with me throughout this entire talk. Shout out to Zara Ali for that. You'll probably see Ferris several times throughout this talk, so keep an eye out for them. Before we get started, I'm going to break down the layout of what this talk will look like. First, we're going to look at an overview of game development, and some of the challenges involved with it. Next, we're going to learn about what the Rust language is, and explore the features that are relevant to game development. We're then going to explore a dominant pattern for game development in Rust, the entity component system. Next, we'll examine the current state of the Rust game dev ecosystem. We'll finish off by looking at what you can do to get involved in this world of Rust. So, first, let's start with the problem statement. Video games are intricate programs that require a lot of planning and collaboration to create. They're real-time applications, and often run in loops that must execute in under 30 milliseconds, or over 30 times a second. Further, games are comprised of many systems working together. This includes AI, rendering, game logic, networking, and many other systems. All of these moving parts operate on underlying data shared between them. We need good abstractions when working on this data. So, to recap, we need to be rendering frames quickly and reliably. Cross-discipline teams working on games need to work on different systems cohesively together. And finally, we need to have easy access to the underlying data. However, we should also briefly set some expectations. I'm going over a lot of improvements to game development that might not be as clear to someone just entering the field for the first time. When developing games with rapid iteration times, such as for game jams, I tend to use a higher level game engine, like Godot. In fact, if you've been wanting to try out game development, the Global Game Jam is happening next week, so definitely check that out. That said, it's important to not try and solve every problem before you know the question. It's very easy to fall into a rabbit hole of over-engineering. And I also want to acknowledge that this talk does have some complex ideas, so don't worry if you don't understand all of it. I'll be available during the whole conference on Discord, so feel free to reach out to me to ask more questions. Now, let's get started with the real premise here. I'm going to start by adding a little more to my intro. So, I started using Rust for my AI assignments at school in 2017. Within the Rust world, I'm currently working on a game called Valorant. I'm one of the core developers of the game, where, among other things, I work on continuous integration, cross-compilation, and outreach. I've edited Valorant's technical blog for over 150 weeks in a row now. I'm also a team member of the Rust Game Dev Working Group. On that team, I focus on editing the monthly newsletter, like we can see here. I also run a monthly meetup and co-host the Rust Game Dev podcast. Now, let's dive into Rust. Rust is a systems language. It's a compiled language and is most often compared to C or C++. However, it has many inspirations from other languages. It borrows from the functional paradigm and also has a strong type system. It's also very expressive. We often feel that it is easier to accomplish our goal in Python than C++, but then inevitably arrive at a point where we wish we had the structure that C++ provided. However, in Rust, we can have the best of both of these worlds. For starters, though, let's try and look at this from a step back. Why are we trying to reinvent the wheel? As I said, Rust is similar to C++, and C++ is already the industry standard for a large amount of game development. In the next few sections of this talk, I'm going to work to show some of the improvements that Rust brings to the table. We'll start with Rust's core feature, memory safety. This is what sets Rust apart from other languages. Memory safety allows us to work with computer memory without the fear of making large mistakes that we've made in the past. From a security perspective, we eradicate errors in the realm of buffer overflows. From the perspective of software engineering, we are safe from double freeze, seg faults, null pointers, and any other undefined behavior. But you might be thinking, isn't this already a solved problem? Aren't I safe in Python or C# or many other languages? And in a lot of ways you are. However, these are also garbage collected languages. This means that periodically, while the program is running, something will have to go around and clean up any variables that are no longer referenced. This can lead to unpredictable stuttering in games. This is one of the reasons that C++ has been used in the game development industry for so long. It puts the job of freeing memory onto the developer. As we can see here, after allocating memory on the heap on line 3, we manually free it on line 9. With this, we don't have to worry about garbage collection. Our games can run fast without a background task running that we can't control. However, we've run back into the same problem we were trying to escape. C++ is full of potential for foot guns, a term that describes having a powerful tool but the ability to easily hurt yourself with it. Nothing is stopping us from making mistakes other than our experience in having made them in the past. There are ways to mitigate these issues, like smart pointers, but that doesn't solve the core problem. To understand how Rust is memory safe, we'll do a quick survey of some of the ideas. This will remain pretty high level, just to stay in scope of the talk, but it should give some context as to what is happening. In this example, after allocating memory on the heap on line 3, we don't need to manually free it later. The Rust compiler will actually do this for us at compile time. Rust's memory model is enforced through a system of ownership. Let's look at the definition from the Rust book. We see that each value has an owner. There can only be one owner for each variable at a time. And finally, if an owner goes out of scope, the value will be dropped. And then we have another term, moving. Moving happens when ownership is transferred during assignment or when passing to functions. So, a few slides ago, I mentioned that you don't need to manually free memory in this example. But I do want to note we are allowed to if we like. What happens in this case when we try to drop the vector twice? We can see on line 9, the first drop happens. It takes v by value, and ownership is transferred to that function. When we try to drop v a second time, we'll get a compiler error that tells us we tried to use a moved value. So, we're properly safe from double freeze. These foundations of memory safety have led to some popular sayings in Rust. The first, fighting the compiler, comes from not being allowed to compile your code until the rules are followed. And I do want to bring my mug back here, because on the top it says, "You have failed your borrow check." And so that's a little bit of Rust humor right there for you. The second saying, "If it compiles, it probably works," is where we are able to reap our rewards from our labor of making sure that the compiler is happy with how we coded. In effect, we're signing a contract with the compiler. By following rules more strict than in other languages, we are able to have more trust in our programs while they run. In terms of game development, this guarantee means a lot. It means that while we're working on large cross-discipline teams, we can trust a compiler to prevent us from hurting others unintentionally. If we can compile the code locally, we can be more sure it will merge with the code of others. Most importantly, this contract spans the entire codebase. Whether code touches several systems or just one, the same requirements must be met. Mistakes you make that affect code on the other side of the codebase can be very difficult to track down, especially without the right tooling. Memory safety gives us another of Rust's pillars, fearless concurrency. This is the idea that if we want to pass code across thread boundaries, we can make sure that it is also memory safe. This helps run parallelized code without the fear of data races. So let's break that down a bit. CPUs today aren't getting much better at single core performance. In terms of classical CPUs, Moore's law is dying. However, the number of cores in CPUs is increasing rapidly. Because of this, the performance in the modern age of computing is becoming synonymous with distributed work. We hear the term horizontally scaling a lot in the modern cloud development. So when we care about performance, we really need to be figuring out how to run our code efficiently and safely across many threads in our system. Next, let's take a look at error handling in Rust. Errors happen when you haven't defined how your program should handle some edge cases that it has come across. Making sure that we're able to handle errors is essential in game development. We don't want our games crashing for players during a multi-hour long gaming session. In Rust, crashing a program is easy. Like in many other languages, you have ways of throwing an exception. In Rust, it's called panicking. However, when you're not actively trying to crash, it's surprisingly hard to have it by accident. As I mentioned before, Rust compiler prevents seg faults. If you have experience in C or C++, you're surely familiar with debugging crashes of this nature. Without the worry of seg faulting from a vast array of reasons, we've already made the error handling task a lot easier. Now, let's look at some areas where programs fail and need to recover. Here's an example of that. We're converting a string to a number. Easy enough. If we parse it to an I32 type, then so we're parsing it to an I32 type, and then we're doing something called unwrap. But what happens if the string isn't a number? Oh no, well, we see that the program panicked while it was running. And we've even got Ferris panicking. Didn't I promise this wouldn't happen? Well, not exactly. I promised that it wouldn't happen accidentally. What the second line says is that take the string and try parsing it as an I32. What I get back from that is a Rust result. And a result can be one of two variants, either OK or an error. By using unwrap on it, I'm saying, I believe that you're the OK variant, and I want to see what you contain. However, unwrapping will panic if it receives the error variant. But this was my fault. I told the compiler that it would always be OK, and I lied. In that case, it's more helpful for the program to crash so that I know an edge case was reached that I didn't anticipate. Here's an example of how to handle this error properly. There is a bit more syntax here, so let's walk through it. On lines 2 through 4, we're now matching against two Rust variants, OK and error. And sorry, these are the two Rust variants. There's no more, just two. The match statement is similar to switch cases in other languages. We're saying that if the parsing returned an OK, we'll take the number out of it and return it. But then we also say that if it was an error, we'll just return 0. The underscore means that we don't want to extract the rest of the information about the error. So, to recap what we've seen, Rust is memory safe as a non-garbage collected language. This has many benefits, including the fact that we can parallelize code very easily and stay away from data races. Finally, we must always acknowledge places where errors can happen by handling them in some way. Now that we've explored some foundational benefits that Rust provides us for game development, we're going to dive into patterns that work well for game development in Rust. When coding in other languages, we're most often familiar with object-oriented programming. We can model data through abstractions such as inheritance and polymorphism. We often hear the classic, a dog and a cat can both inherit attributes from animal. Rust, however, is not an object-oriented language. It does have structs and can be used to model data, but there's no polymorphism or inheritance. However, we do get a lot of power on top of Rust structs. We can define methods in the context of structs. In this example here, we're creating a rectangle struct. It contains a width and height, both of which are 32-bit integers. We're then implementing a method area in the context of the rectangle struct. This method multiplies the width and height and returns the result. Now, let's take a look at the main function of this program, starting on line 12. On lines 13 through 16, we create an instance of the rectangle. Then, we pass the area of the rectangle by calling it as a function on one of the instances, or on the instance. So let's take a look at how it runs. So we can see here that it returned the area 12. And so from this, I'm able to very easily see that by implementing this method on the rectangle, I can pretty easily implement some functionality on types. In the game development world, historically we've built games that follow the object-oriented paradigm. Let's see what we can do in Rust instead. We're going to take a look at the Entity Component System, or ECS. ECS is an architecture pattern. Let's break down what an ECS is. At its core, an ECS is just an API that gives you a way to access and manipulate data from arrays. An ECS follows the principle of composition over inheritance. By this, I mean instead of creating entities that inherit from a base class, entities are built using components. We can break down ECS into its three terms: entity, component, and system. Starting with entity, we have just an ID. What an entity is gets defined by the components that are attached to it. So we keep the idea of entity as lean as possible. This also means that any base entity can take the shape of anything, whether it be a cat, a sound emitter, a tree, a car, or anything else we might call an object. Next, we have components. This is where all the data goes. We can think of components as the entity has a blank. Entities have an arbitrary number of components, all of which represent different types of data. And components of the same type store the same data regardless of the entity they're attached to. For example, a position component might include x and y integers, and any entity that gets this component will then be able to store its x and y position. And finally, we have systems. Systems allow us to query and manipulate data. A system works on components mostly outside of the context of what they make up. For example, I can ask every entity that has a position component and velocity component, and then update the position based on the velocity. In this example, I don't care what the full entity represents, only that I need to update everything that has both the position and velocity. This allows us to cover the object-oriented programming case of a dog and a cat, since both of those would have position and velocity components. Although there are different ways to implement an ECS library or framework, one popular way is one that resembles the design of a relational database. So we can kind of compare it to a relational database, but without the need to store it to a disk. Each entity has an ID, and then also stores IDs of components that it has. Components can then easily be stored in their own tables, or more often arrays. So let's take a look at what some sample data might look like with an ECS model. We have 4 entities here, with IDs between 0 and 3, and we can see them in the top row. We also have 4 components that we see on the left. Now, I want you to try and think about what each entity could represent. Remember, we're thinking in terms of entity 0 has a position, velocity, and health. But we're also saying that it doesn't have an AI component or a mineable component. Also, the implementation of these components is unclear, so it might represent more than one thing. When I created this diagram, I was thinking that entity 0 could be a player character. It needs to move around the world, so it needs a velocity. But it doesn't need the AI component since it's playable by a player. And then if we look at Entity 1, I consider it to be a non-player character that is in the world, maybe someone you get a quest from. And in our imaginary game, the NPC characters can't die, so they have no need for a health component. Entity 2 is a bit different. It doesn't have a velocity component, but it does have a health component. So what could that be? In this case, I imagined it to be a rock that you can mine from. This is why it has a mineable component. A system could iterate over each entity that has the mineable component each frame, and if it has received damage, maybe drop some resources near it. Finally, we have Entity 3. It's similar to Entity 2, but doesn't have the mineable component, or the health component, and I imagined it to be a tree in the world. We don't want the player to destroy beautiful trees in our towns, so it doesn't have health, and all it needs is a position. Entity component systems not only allow us to model data differently, but also operate on it rapidly and safely. One reason for this is how easy it is to parallelize with different CPU threads. Let's say each frame we need to update the position of 10,000 entities based on their velocity. It's very easy for us to send the first half of this to one thread and the second half to another thread, or we can even divide it down further for how many threads there are available on the CPU. So, to recap, entity component systems are an alternative to structuring data in an object-oriented way. We can say that entities have a certain component, or several of them. Systems are also able to pick and choose which components they run on. Finally, we'll end off this talk with a look at the state of Rust game development. As with many domains in Rust, the best place to search for information is Are We X Yet? And in this case, the game development ecosystem can be explored at Are We Game Yet? This site shows a lot about games being developed in Rust, as well as tools and other crates. So, as you can see here, we can view crates available from many different categories relevant to game development. And so maybe we can go here, we'll take a look at all of the ECS options. So as you can see, there's quite a few different crates that implement entity component systems. In the area of game engines, several large projects are paving the way. The most popular right now is Bevy, which just released its 0.6 version. Bevy focuses on the idea of the entity component system controlling everything about the engine, from the data to the UI to the renderer. It took the Rust ecosystem by storm, as it is built from the experiences of existing engines. There are also several other engines that are quite popular. Fyrox has a scene editor that already allows for very powerful 3D world creation tooling. Amethyst has been a staple in the ecosystem for a while, although is coming to the end of its maintenance cycle. In terms of the industry, there is currently one company that is pushing forward quite heavily in this space. Embark is a game studio in Stockholm, Sweden, that is working on a dozen or so open source projects in the game development and graphics ecosystem. This is to help them with games that they are developing, but it also pushes forward the agenda on what others can make use of. One of their major projects right now is Rust GPU, which aims to allow shader code for the GPU that's written in Rust. Now that we're at the end of the talk, I want to show you some ways that you can get started if you like. I highly recommend starting by reading the Rust book. It will give you a good foundation for the rest of the language, and explore principles I've discussed here in much more depth. Going through the Bevy tutorial can also be a good way to get introduced to using the entity component system. Another opportunity is looking to contribute to Valoran or other Rust projects. In fact, many of Valoran's developers started using Rust for the first time to contribute to the game. There are many areas that don't require too much experience to get started with. We've recently been running what we'd like to call the Valoran Reading Club, where one of the core developers breaks down some of the more intricate systems from the game. I want to wrap up with a quote I heard somewhere in the Rust ecosystem. One of the biggest features of Rust that I haven't mentioned yet is its community. People are always willing to help beginners, and so much work is done in the open that is and is accessible, so you can even see what the deepest parts of languages development look like. So if you want to get started with Rust, remember, if you think you're a Rustation, you're a Rustation. If you think you might be a Rustation, you're a Rustation. And with that, we've arrived at the end of my talk, Leveling Up Game Development with Rust. I wanted to shout out my technical reviewers for taking a look over my slides and providing some great suggestions. If you want to ask questions, I have a few minutes here to answer some, but I'll be available on Discord this whole weekend, and happy to chat about anything you want. Thanks, and enjoy the rest of your weekend.